Hi everybody, welcome to one more of Mrs. John's lesson. This one is concentrating on solving problems on torque. Now there are three possible ways or types of questions based on torque. One of them is when you have the pivot at the center, and so the red dot is the center where the mass of the whole object, the seesaw or the ruler or the bridge or whatever it is that has been pivoted, acts. So if you have, let's say you've got two people sitting on the seesaw, so there's one over here, and then there's another person, maybe a larger person over here. So in order to balance them, because their masses are different, their distances from the center is also going to be different. Usually one of the first questions that's asked when you have one of these is to identify the forces that are acting on the seesaw. So there's actually 4 force vectors that you need to do. So this is what you need to do. So there will be the weight force or the gravity force of this person, and let's call this person 1, that is person 2. So weight force of this first person is the mass times g, and the weight force of this person will be F2. A longer arrow, this person appears to be bigger, more mass, M2 times G. And then there is the mass of this ruler itself that acts through the center, and that's also some sort of mass times G. In addition to this, you cannot only have downward forces, you also need upward forces, and the upward force that acts here would be the support force provided by the pivot. And what we need to remember is that the total upward force is equal to the total downward force. In addition to this, in order to calculate something, you usually have to find either the distance or the mass of the other person, something or the other, and you're always given the length of this. So, and all distances are calculated from the pivot. So if I call that x1 and if I call that x2, what you will find is that m1g times x1 equals m2g times x2. Okay, and if you use this relationship, you should be able to calculate whatever has to be found out. The nice thing about this is because g is common to both, you can take g off if you're not asked to find the force, but if you're asked to find the distance. So that's one type of question. The second type of question is when the pivot is not at the center. So the pivot needn't be at the center, it can be anywhere, but there's only still a single pivot. Now I want to demonstrate that using just a meter ruler and some masses that I have here with me. So I'm just going to do that here. Okay. So the first thing I need to do is I've got a meter ruler. I want to find the mass of this meter ruler. It is 79.9 grams. Okay, so let's call that about 80 grams. That's the mass of the meter ruler. Just going to remove this scale. All right, now I'm going to put this meter ruler across the edge of my table, and I'm going to put it quite far away from the table. So I'm just going to bring this here so you can see what I'm doing. Okay, so let's say there's a plank and the center is here, so I'm going to put it beyond the center. If I let it go, it's going to tip. To prevent it from tipping, let's say you've got one person standing here. So I've got some masses here, and let's say there's another person who is walking along this ledge that is protruding out. So that's the other person, so their masses are not the same. So each of these slotted masses is 50 grams. So I've got 100 gram mass over here, and at the other end, well, to make it even more accurate, I will just put that, do this. So that's 50 plus 50, 100, 150, let's make it 200 grams. Okay, so there's a person of twice the mass who is walking along there. Okay, so I'm just going to slide it all the way. Okay, and he keeps walking till it's about to tip. So when it's about to tip, just about to tip, we say it's at equilibrium. All the forces are balanced. So this is the 500 gram mass. That's where the mass of this ruler acts through, but you can see it can go beyond that. It's about to tip. Can you see that's about to tip? Okay, so at equilibrium, the forces are balanced. So this, can you see the ledge, the end of this is the pivot, okay? And that is at the 400 millimeter mark or the 40 centimeter mark, and all distances are measured from the pivot. So the distance of this mass, let's say that's Kate, the distance of Kate to the pivot is 400 millimeters or 40 centimeters or 0.400 meters. The distance of the center of mass from the pivot is 500 minus 400, which is 100 millimeters, 10 centimeters or 0.100 meters. And this one is about the 560 centimeter mark. So we can actually find out what is the distance this one has to balance, okay? So can you see? So that's how you can have one pivot. So let's just look at some numbers and let's see if we can solve this problem. So I'm just going to flick back to this question here so you can see. Okay, so that's the scenario. So we had, so the force is acting. So we have somebody who's over here, and then we have someone who is over there, so that it's just balanced. Okay, where is the tipping position? So the tipping position of the pivot is, this one is the pivot. Okay, the distance from here to the pivot is 40 centimeters. The distance from the pivot, so all distances from the pivot, the distance from the pivot to the center of mass of it is 10 centimeters, and and let's say we have to find that distance. Okay, where is that balanced? Okay, and so for that we need to know a few things. So first of all, let's just get all our force vectors. So there is this gravity force of the mass of this acting, which we found was about 90 grams, or 0.090 times 9.8. And then this was 100 grams. So this was 0.100 times 9.8. So that's your gravity force, weight force. And this one here, it's a longer arrow, just longer. So that was 200 grams, 0.200 times 9.8, and let's see where this tipping point is. So at equilibrium, the sum of the clockwise torques equals sum of anti-clockwise torques. Now to figure out what's clockwise and what's anti-clockwise, it's always from the pivot along this beam. Okay, so this is your beam, my meter ruler. From the pivot along the beam, I get an anti-clockwise torque here. From the pivot along the beam to the next force arrow, I get a clockwise torque, and then there's also another clockwise torque. Now, in addition to the downward forces, there's also the support force that's provided there. Okay, so that's the support force acting through the pivot. All right. Okay, so let's find out what this is. So my anti-clockwise torque is 0.100 times 9.8 times 40 centimeters, so let's just put that in centimeters for now, is equal to, you got 0.090 times 9.8 times 10 centimeters, plus you got 0.090 times 9.8 times x. Okay, let's see that one there. Okay, so when you multiply, so let's just cancel all the 9.8s because it's common to every term. So you get 0.100 times 40 equals 0.090 times 10 plus 0.090 0.200 times x. Okay, so that's the one that we don't know. So let's just get everything that we know to one side. 0.10 times 40. So let me just get my calculator. So 0.100 times 40 gives you 4. And then minus 0.090 times 10, 0.09 times 10 will give you 0.9, minus 0.9 equals 0.200x. So 4 minus 0.9 is 3.1 divided by 0.200 is x. So if I just go 3.1 divided by 0.200, I get 15.5 centimeters, and that's how far this one is from the pivot. Okay, right. So I'll just stop.